Good. So the purpose of today is to just establish general awareness of what contingency estimation is. People like to call it QRAs and things like that, but it's really about estimating contingency that we're talking about today. And it's the high-level principles. We're not going to go into the detail. That will be the topic for future sessions. So just to set the scene, I'm not going to teach you about specific QRA methods today. We're going to introduce various aspects to set the scene for future webinars. Okay, so I'm going to talk about the general concepts. We're going to have some fun with some historical data, contingency estimates. There'll be a few polls coming up, 2 polls coming up fairly soon, so for which I would suggest that you record your answers on the first poll, because the follow-up poll is going to ask you questions about this first one. So maybe just be ready to do a screen grab of what your answers were, or if you have a good memory, that's fine, or grab a piece of pen and paper that you can just note your quick answers, the options you selected. Then once we've gone through the historical data, I'm going to go through RP40R08, which is basically the one that sets the background for contingency estimation. Now, if you're not an AACE member, it doesn't matter. You don't have to be too concerned about that. It's just, I'm going to take you through the general principles that's in there. Okay, good. So now we're going to talk about project performance, history, and contingency. Why do we need to have this contingency thing? And why should it not be just the magical 10%? So the first thing is I'm just going to quickly step over some definitions. So if we start from the left, cost is an amount that is essentially measures the investment of resources that you've spent over on the project. Contingency is an extra amount that's added to an estimate. It depends on the state, the occurrence of uncertain effects will likely result. Basically, it means it is money that is expected to be spent. Now, obviously, an estimate is a forecast of the probable cost, and it is tied to an agreed scope. Then the management reserve, which is a word that some people are not familiar with, or a term that they're not familiar with. It's basically money that's outside of the contingency and the estimate, and it's not normally expected to be spent. Expected in this case, 100%. So if there's like a 50% chance of you spending it, it most probably should be a management reserve item. Good. So this slide, we're going to start the first poll now. So you're going to get a first question you're going to get is just to pick an industry with which you're familiar. There's also an option for another industry, and whether you're totally inexperienced or don't know, or you've worked in many and you can't make your choice today. The reason for those specific polls is we've got some data on the first 7 categories that we'll share with you. So the first question that you're going to be asked is, what percentage of large projects, and I don't think the question on the poll actually says a large project, but we're talking large project now, $100 million or above, is completed on budget at authorization. So the budget at authorization, not the 6 baseline that was done a month before the project was finished, the original one when the investment committee said you can go and invest. How does that compare to what was finally spent? Then the next question is going to be a bit of a ratio question. This is why this picture is in here. And I'm asking you, what's the ratio of A? Can you see the cursor? Maybe I should just, I'm trying to remember.
Yes, we can see the cursor.
I can't remember where I changed it yesterday. Oh, it was here. Laser pointer. Okay. So the question is, how much is the second portion of the curve, the portion above 50% chance of finishing? What's the size of that portion to the 90th percentile over the first section between P10 and P50? So please, you don't get fixated about these numbers. On here is just an example graph. It's a bit of a red herring there, but the hot tip is your answer should be slanted to the right. Okay, and the last thing is this line here on the side is a 90 percentile line. So your question here at the bottom is, how confident are you about your answers? And you should aim, for you to pass this test, you must be 90% confident that your ratio and your first question is correct. Okay, we can run the poll.
Thanks, Martin. I've launched the poll. So people can answer as we go. Once we've given them a couple of minutes to go through the answers, I will end the poll and then we'll be able to see the results. What's your expectation, Martin, in terms of number 2 and 3?
My expectation is dismal failure. So it's good thing that I don't know whether Anton can vote, whether he's here, because he saw the slides. All the other people who saw the slides are on the panel, so they can't vote. So they can't cheat.
Okay, people are fairly slow to vote. I'll give them another 10 or 15 seconds.
And as I said, guys, remember it's anonymous, so you're not going to be embarrassed. You yourself will be the judge of how badly you judge. But don't feel bad if you get this horribly wrong. This is par for the course, as you will see from the results that I'm going to show you. And typically, it's also par for the course for if you do a proper QRA workshop, that people get the range of the realm of possibility completely wrong.
Okay, another 5 seconds, and then I'm going to close the poll. So if you need to push a button to submit your questions, please do so soon. And I'm going to end it, and then we can see the results.
Okay, so most people are in mining and
process.
So the ratio people, so people believe that most of the projects finish 20 to 50% of the project finished on budget, and I think the ratio is 110 to 150%. Okay, so they believe that overspent is 20 to 50%. Good. Okay, so I've won. Because here's the results. Okay, so what you'll see on here is essentially if the number is a negative, it means that gives you a rough indication. So for hydropower dams, that's dams in Canada, the number is somewhere in the region of between 15 and 24% of them. Well, it's a fairly low number that completes on budget. Mining and metals, also a fairly low number, depending on the two. There's two different studies that we used here. Pipelines, that's linear type infrastructure. They overrun a bit. On the bottom side, they do run. They can come in under cost. Process industry runs very wide. Some of the studies show that they're very close. The first two don't look too bad. But look at this one, done in 88, overrun by 190% at the top end. Transport and rail, very wide range. Water projects. Okay, so although 20 to 30% overrun on your project might not result in financial ruin, if you get something like 120% or something at the P90, you will have a problem. You'll get fired essentially in the end if you didn't get fired before that. So the reason for why some of these numbers are in yellow, I just wanted to highlight to you. So the ones in yellow on the right-hand side is obviously the overruns, which is obviously bad. But what people sometimes forget is that the significant underrun is equally bad because it keeps money away from other projects. Good. So now the second poll. And now I want to just see how dismally we failed. I think Yeah, we can launch that poll quickly. Just give them like a minute to answer, Werner.
Your expectation, Morten, does it meet your prediction?
Well, most of the people say they didn't fail the test, and they believe that they got it reasonably correct. Okay, let's go on. Good. So on the results slide in the previous one, I showed that curve there, and I didn't talk about it. The red line is typically what projects estimate for large projects, and the blue line is what the truth is. And you can see that the tail is very, very long. The numbers go up to almost a 4 here on the right-hand side. Okay, the graph that's the main graph here on the screen is for small projects. This is the type of projects that typically run on a plant or a little project that typically like a municipality might do or something like that. They tend to run in well under budget, and if they overrun, it's a very small overrun. It's called this, they typically refer to this curve as a cresting wave. And what this means is that on your small projects portfolios, you might have a lot of money tied up into estimates because remember, they fund at the one and then finish up early. So they end up building in so much fat that they tie up CapEx for other projects. Good. So let's just talk about what's contingency for and what it should be used and what it should not be used. Okay. Just want to turn this thing off. Good. So can be used for errors and omissions in the schedule and the estimate. So that's the normal things. You forgot you're supposed to buy 100 PCs, but you only got 90 on them. It's not going to break the bank. Normal price and quantity uncertainty. You're not exactly sure how big your project team is going to be, but it's a $100 million project. But you might have 2 or 3 extra engineers that you need to put on the job. Or your steel quantities and things like that is slightly uncertain, but it's not a major issue. Changes within the existing baseline. Within the existing baseline, people. Market variations, systemic risks. Now we're going to get to the definition of systemic risks a bit later, but it's essentially something that should be on the risk register. Project-specific risks, which are included in the contingency estimate. That will become clear now. Schedule delays and the risks associated with that. Remember, time is money. Okay, what is not in the contingency? Because this is typically what you see people want to use contingency for. They want to use it for new scope. They want it to fund abnormal price and quantity fluctuations. Changes to project strategy. If you change your project strategy, if you change your packaging, if you change your engineering contract type and those kind of things, you can't use your previous contingency estimate to fund that. Force majeure events, insured events. So if you've got insurance for fire on your construction site, something like that, it shouldn't come out of your CapEx, it should come out of the contingency. It shouldn't come out of the contingency, it should come from insurance. Project-specific risks excluded from the contingency estimation process. So if you said that there's going to be no geotechnical risks that hit you, and they do hit you, you should go and ask for new money, not for contingency. Management reserve and large risks with their own contingencies. Okay, so this is really about the concept really is you don't include in your contingency items which are so large that if that specific item was to happen, that it will wipe out a large portion of your contingency. So if you have a risk that contributes like 30% or something like that to your contingency, rather make a separate provision for it. Then escalation and Forex. And we'll get a bit to that a bit later. Those escalation, Forex, and management reserve, they can have their own separate contingency, separate from capital. Okay, good. So I'm going to start talking now about the estimating principles under RP. So I think the first thing that one would just need to remember when you're talking about contingency and the whole process is because how you're going to, as I'm going to talk about it, you're going to come up with the question is, how much is enough? How good does my calculation have to be? When do I stop the risk guys, paralysis analysis and those kind of things? And the answer really lies is, can you make a good decision? Will your decision to go ahead with the project or not change if you have more data? If there's a good chance that you won't change your decision, then you stop the process there. Okay, so then it's also good to remember that what we're talking about today, people normally associate contingency and the processes applied to contingency estimation with setting a baseline for a project, funding a release, or for a revised baseline to figure out what the CapEx and maybe the schedule contingency is. But these techniques can be used for bid adjudication, option selection in FEL 2, strategy evaluation, claims analysis, all those kind of things. So there's various other places where this can apply. Good. So now we're going to get to RP 40 R08, and we're going to talk about the general principles that's tied in there. And people, these principles, even if you don't subscribe to AACE principles and RPs, these are very relevant to wherever you are. They are applicable to industries that's not covered by AACE. They just make good sense. Good. So we're going to get into these into detail the next slides. So there's a couple of principles. First one is you must meet the objectives, expectations, and requirements for which you are doing the contingency estimation. It needs to form part of a decision-making process. Basically, if it's just going to end up in file 13, there's no point in doing it. It must be fit for use. Some techniques are better suited in certain cases than others. It must start with identifying the risks. You must be able to clearly link your risks to the schedule and cost outcomes and to the contingency. There's a whole story behind that we're going to get into. You shouldn't introduce risks by the method that you use. Make use of empiricism, i.e. historical data. You must use an experienced and competent risk analyst. This is a huge issue. We'll get into it a bit later. And we must be able to link probability to the output. Good, so let's start on those first ones. Okay, so to meet the objectives, what's the main thing? So we need to consider, why are we doing this? Are we doing it for funding release, or are we doing it as a bit of a dipstick test halfway through a FEL 3? We need to understand that, because it will determine what level of effort we need to put in and what method we choose and all those kind of things. Then you need to be very much aware of the governance requirements, terms and definitions of whatever for the specific company or a consultant or your own company. What do I need? You might like to, you might believe that a P50 contingency would be great, because then I know I can get my project approved, but the board actually wants, they're very risk averse and they want a P90. The method that you're going to use for the contingency estimation should be validated before you start. You must agree on the method and not just go into the workshop or wherever, come up with a number and then somebody say, I don't agree with the way you did this. Okay, risk tolerance, we already spoke about that. Okay, so this contingency estimation process must be part of an effective decision-making process. So what it means is you need to understand how this information will be used. Afterwards, when is it required? Do you need to determine the contingency before they finish the design, or only after the design, or when 80% of the procurement's been done? All those kind of things that you need to understand. Who needs to have insight into the calculation? Does the finance department have to look at it or not? Do you have to have a third-party review of your contingency estimation afterwards? So those are all important aspects to consider. You need to, the deliverables that you produce from your contingency estimation need to support what the process needs. So if the process says, if the requirement is that you need to produce a graph and some sensitivity analysis, don't just quote a number and say it should be 15%. And important, if you deal with somebody, if you're a consultant or somebody, or if you're working in a company and you don't have a process to decide or wherever how it works, define something, put it down and say, this is how we're going to do it. First of all, this is how we're going to do the contingency estimation, and this is how we're going to apply it throughout the project life afterwards. Okay, fit for use. You need to consider, if you're doing it on a portfolio program or project, you need to consider what type of projects it is. Because, for example, a software project and a large civil construction with a lot of excavation is radically different from each other. And the type of work and the complexity and everything is different. So the level of technology involved in the process and the project, what the scope of the project is, will to a large degree determine which of these methods you can apply and which not, and how you should apply them. So the risk type that you are exploring, strategic or tactical, systemic or project risk, those all are relevant. The phase in which the project is it in phase 1, 2, 3, 4? Where is it? The estimate and the schedule basis, those are very important. They often give you a lot of indication of what is in and what's not in. Sometimes they're poorly documented, but it is a very useful document. It is one of those documents that you really shouldn't go into a contingency estimation for a baseline without that already being finalized. And the methods that you use must fit the skills and knowledge of the practitioners and the participants in the process. So no good having a QRA and the other people don't understand it, or you have a project to maybe refurbish a whole truck for a mine, and you put a young engineer on the job who's got 1 year's working experience. He's facilitating the session. He's going to do the calculation, and you've got the accountant on the team and the civil engineer on the team and the tea lady. That's not going to get a good result. And people sometimes do the equivalent of these things. They forget that they should have an estimator in these sessions, for example. Good. So start with identifying risks. So it's important that you need to identify the risk that you need to analyze and not start the other way around. People tend to want to say, there should be a 10% contingency that we get out, so what risks can add up to 10%? And things like that. There is a concept of critical cost elements that's discussed in one of the RPs. I'm not going to really get into it. It's sort of related to a Pareto analysis, but Pareto looks at the ranking of the items in terms of total value, whereas critical cost elements are interested in the ranking due to variability. So you're looking at the items that can which will, by their variability, have the biggest impact on the total cost of the project. Total cost, we're talking about CapEx, escalation, and Forex allowances. And the escalation one is a big one that people get wrong. And you could even go as far as to say that you want to do it on the financial model. Then you're going to get or add OPEX and revenue into that whole thing as well. Good. And people, please, if you have a financial model, go and look at what it says. Even if it's a preliminary model, go and look at what it suggests are the top things for the business case. Because you might find that schedule is not important to your project and OPEX is important. So therefore, you should be more worried about the OPEX side of the risks than the schedule risks. Okay. So we need to be able to clearly link risks and schedule risk to the schedule and cost outcomes, because we need to understand how they come from and we need to be able to explain it in the end. So, and what you will find, that first bullet, is if you've ever done or participated in some kind of a contingency estimation, especially if you are talking about simulation methods that we'll get into a bit later, you'll find that if you take your risk register that you had before the meeting and what you discussed about your risks afterwards, you will find that what often happens is the probability is not somewhere close to 50% for a specific risk. It might be closer to 10%. And the impact is a much wider perhaps than what your heat map had originally suggested. Because when you start figuring out, when you start looking at where does this thing impact my schedule, you start realizing a couple of things. And one of the things that also happens is that you can identify perhaps the schedule impact of a risk, but you don't know how to quantify the cost impact of that on P's and G's and everything. And that will be an answer coming out of your QRA. You must be able to demonstrate the contribution of each risk. And we're not going to get into that, but your typical tornado diagram that you get out of a QRA doesn't really tell you the true picture. Because the question that comes up often is, you see the number, the results tell you the project is going to overrun by 80%. And the next question then is, what must I change? And then you must be able to say, this risk we need to change, that, and then that one. Good. Good. So the method shouldn't be introducing risk. It's important to make sure that you get the vital few correct. That's those critical cost elements that I spoke about, because those are the ones that can really dominate. So you shouldn't make any mistakes on them. So even if there's no uncertainty on your critical cost elements, you need to be able to stand there, hand on the heart, we did go and look at it. Engineering confirmed that the design is correct. The estimators confirmed that the price is correct. So the people can calm down. We don't need to worry about the results coming out of this. So the other ones that typically happen is people underestimate the risk impact. Then they end up with insufficient contingency. They overestimate the risk impact. So they take funding away from other projects. So those are typical things that happens then. Okay, making use of empiricism. Okay, you should make use of data wherever possible, specifically for systemic risk, and we'll get into that when we talk about parametric modeling methods. You should look at lessons learned, what risks has happened, how bad did it happen, benchmarking results, probability and impact data for past projects, but beware that sometimes the data can lie to you. I would hazard a guess that most of the people on the call, or most probably all of them, nobody on the call has possibly ever had your house burned down. But that doesn't mean that it doesn't happen and that you should go and cancel your fire insurance on your house. Good. Experienced and competent risk analyst. Now, I have a bit of a bugbear about this, but this is not my words. These comes out of AACE documents and out of articles published by John Holman. So essentially what it means, if you use the wrong people, you will get the wrong results. It is important that your analyst for these continuous, especially for the simulation methods, must be experienced, must have worked a while, must understand quantification, must understand the operational side of the type of project. So if you've got a mining project, the person must have worked in mining operations. If it's a software project, you must have worked on the other side, not just on the software development side. Should understand how projects work, should have competence in training and hands-on experience. And it all goes to how big is the danger if they get it wrong. That's what you need to decide. Good. Link probability to output. Okay, so the client, when you communicate the results, they need to understand what the uncertainty is. They need to understand what drives it. If you can't produce a distribution curve, which I'll show you some of them later, you need to at least communicate equivalent information. Bernard, I see I'm starting to run out of time. I'm going to speed up a bit. The communication one right at the end. Good. So let's talk about systemic risk and project-specific risk. The first one, systemic are those features of your project. If you remember here, that we would call noise in the system. So it's like your productivity of your people, your interfaces between your system, how your project organization work in your company. It's maybe the conditions on site where it's hot, or you're working in a country where it rains a lot. Those are all things which is par for the course. They are going to happen. They must probably have 100% chance of being experienced on any one project. So those are systemic risks, and they are notoriously difficult to estimate when you want to try and quantify them. And then you got your project-specific risks. These are discrete events with typically a fairly low probability, and you are interested in the ones with a large impact on the project. Good. So there are roughly 4 classes of methods in the RP. First one is expert judgment. That's why I got the gray beard there. Then the next is predetermined guidelines. Then there's simulation analysis and parametric modeling. So expert judgment. You need an expert. And they must have relevant experience, and they must use, they can be used to estimate a range of values. Okay. If you have a suitable expert, you can use them. It is highly subjective, the results that come out of there. They typically use rules of thumb. Finding the expert is obviously a problem. The competence, how do you know who's your expert? That's always a big issue with these things. And the thing is, if you ask the same guy the same question next year, he might give you a different result. Or if you ask a different expert an opinion, you get a different result. So that doesn't mean that we can't use this. We can use this for quick decisions on specific areas. So if you want to know how long it will take to do a certain excavation, maybe ask an experienced civil foreman, and he will give you an expert opinion. You're also going to use expert opinion in some of your simulation workshops, but it doesn't mean that but this is now, go to the greybeard and ask him, what should the contingency on my project be? This is what it's primarily used for here. Good. Predetermined guidelines. So these are the famous tables that everybody sees. If you've studied the project management course somewhere, they'll tell you it's 10% at FEL 3, which is a lie. So you can use guidelines, but you must they must be developed for your specific case. They can make provision for contingency for specific risk, but then you've got to add them as a table and say, if you have geotechnical conditions, we'd like you to add 1%. And that's typically what needs to be there. They can be developed by using a parametric model and expert opinion. Okay, these predetermined guidelines are not useful on large and mega projects. But on other projects, they might be useful if you don't have anything better to use. They can be used as a sanity check. If you're a reviewer of projects, contingency estimates, you can use them as a sanity check of where does the number fit. That comes out of a different method, but they should never be used as a way of justifying a lower contingency value. So the QRA simulation that we did, took us a month to do, said 15%, but the guideline says 10, therefore make it 10. No, that doesn't work like that way. Okay, these values are only applicable to the total base estimate and schedule. So it can tell you how much the total estimate can be over, but not on a package. It can tell you what's the finish date when you hand over the keys, but not when you have an interim milestone or somewhere. They can't give you those values. They can't tell you what to prioritize. That's the big thing. What do we need to fix? You can't tell that. Okay. So from an assurance perspective, this is difficult. People often abuse this. They tend to want to use a general thing that they got out of book, not something that's specific to the company. They implicitly state the systemic risks, but they don't state what's allowed for in there, how much of it is for systemic risk, because it's important what you can use your risk for, your contingency for. Good. So let's go into simulation analysis. We've got 10 minutes to go. Okay, so it's typically based on a schedule or estimate to which risk and uncertainty is added. Now, Dave will be demonstrating some of these things, but afterwards, so if you're not sure what we're talking about, you'll be seeing some of that coming up now. Okay. So your uncertainty of your risks are quantified in terms of ranges of possible values. And that's typically where the big pitfall comes. And remember also the probability of the risk needs to be quantified. So you then enter it in some kind of a model and you run a Monte Carlo type simulation. Monte Carlo is just one of the ways of running these simulations. There's many others. So that's why I said Monte Carlo type. So if somebody says to you he's using a Medicine twister, that's also allowable as long as it's a sampling technique. So these are typically referred to as QRAs, but in fact, all the methods that we're talking about here today are a form of quantification of risks. Okay. This is the technique that you should be very cautious of. This is where you can very quickly find yourself in the realm of a fool with a tool unless you know it. So it requires a high degree of expertise in the facilitation and the analysis of the models. We've gone into that. You sometimes use some rules of thumb. It is labor intensive and costly. It can be very complex. And if you know anything about stats, the central limit theory, basically you can get you can get false results if you don't do it correctly. And one of the key culprits there, people forget correlation. Okay, this one requires an expert to review. And to do it well, it is very important. Because most people don't even understand how to read that graph, regardless of how to look at errors that can be in the models. So there's typical simulation methods that's in here. Critical path method. There's range estimating, which really requires expertise. Then there's risk factors, which sort of relates to systemic risk and parametric risk assessments. And then there's expected value. This is the one that you see forms of in your handbooks that tell you, take the risk probability, multiply that by the impact. You get a number, which is called an EV number, and you add them up, and you get your contingency. It's the general basis of that, but there's way more than I just explained, because what I just mentioned is the wrong take out from the process. Please bear in mind that the following items are not recommended practices because they result in, they don't meet those requirements that we got up front. Line item ranging, this is one that you often see guys doing on estimates. They take the estimate line by line. They say to this item 1, we add 1%, item 2, we add 5% contingency, and they calculate the values, they add them up. That's the one version of that they do it. The second is they put the range to every item in the estimate, stick it to a Monte Carlo simulation and produce a result, and they say this is the contingency. Problem with those two are you ignore the risk, you ignore correlation, and it's highly subjective to the estimator's view. Those typically are way underestimated. The other method is reference class estimating. This is basically you look at performance in your industry and you pick a number on the P90 for that. The problem with that is you don't have a clue what you need to fix, and you get these huge estimates. Good. Parametric model. Now, we've spoken about this one a couple of times quickly. Excuse me. So this is typically a form-based model into which you enter project properties. I'll show you an example of what they look like. And it's for systemic risks only. So these are those noise features that's in your project. They produce a single output. So they tell you these systemic risks will add 15% to your project's overall CapEx, but you don't know what of that 50% comes from which of these parameters. The model must be developed involving regression analysis on project historical data. So please don't go and identify a list of systemic risks and decide for this one we'll add 2%, for that one 1% and whatever. Don't do that. That's not going to get the right results. And even if you've got a model that you inherited somewhere, you should ideally test it against the actual performance in your project environment, because you might need to calibrate it. So for smaller projects, the kind of things that you typically do on a mine or in a factory or in a municipality, they might be context sensitive. So you will, the IT project and the building project will have different parameters and different curves. For large and mega projects, regardless of what they are, where they are happening in the world, whether they're building rockets, building a bridge over a river, or a ship, there's a couple of factors that always drive them. And the reason for that is there's those long tails that's on the mega project. Okay, so, and it's important you get schedule models, parametrics, and costs. Now, on your small projects, the cost model tend to be the more useful one, because they tend to not be that schedule sensitive. On the large projects, it's a good idea to look at whether you should add a parametric model for the schedule effects as well. Good. So the good news about this one is it's very easy to use with minimal training. Assurance perspective, very easy to do. It's important that when you get the model, you need to put in the effort to make sure that you got the right model. And then sometimes people would not trust this because it was so quick. You know, you talk about a complete parametric assessment might take you less than 10 minutes. So this is what these things typically look like. Like questionnaire type forms. This one on the left is the RAND corporation model. You enter a few parameters. It spits out a number here at the bottom, which is a standard deviation. On a curve, you need to do a bit of a calculation to get a distribution from that. The other one was developed by a guy called Matthew Schoenhardt. You can find Matthew on the internet on data-driven risk. He also runs quite interesting videos on LinkedIn. And this is what his looks like. It's a form. He develops them specifically for on your data set. You click the fields and it produces a curve and everything for you. So that looks very nice. So then we're going to get into the last section now, is just talking about the RPs. These are going to be in the slide set. These are the relevant ones. We've spoken about the first one that's listed in all of these. There's a new RP coming out very soon that describes how you can use a parametric model, like the one I just showed you, to develop fixed guidelines. So if you have a parametric model, you can develop a informed guideline for your specific scenario. There's some detail on parametric models, simulation analysis. The first one that's in gray, the range estimating one, that is, if there's one that you need to be careful of, it's that one. It's a very good method, but you need a serious expert to facilitate that one, because otherwise you're going to just pick a number on the range, and then you're going to get the wrong results. And that's number 6 that's highlighted here. We didn't really talk about it, but I just alluded to about how important escalation is. There is a guideline out for that. We should do the contingency estimates on the escalation, because it needs to go back into the CapEx. Now, the one thing that I didn't get into, and I'm not going to get into now, is what people normally do is they do the CapEx on the contingency on the CapEx, and they calculate the schedule. Then they give it to the estimator to go and calculate the escalation, maybe some Forex exposure, and they come back. There's something wrong with that process, in that the accuracy of the estimate should include Forex and escalation changes. We never tend to come back and put that value, that revised Forex, revised CapEx, revised escalation into the total CapEx and re-measure the accuracy. Good, so maybe I should just, okay, yes, conceptual comparison, all these things. Okay, now this is based on a bit of an article from Matthew Funart and my subjective interpretation of it, but it's meant to just give you an idea of which fits in where. So in terms of accuracy to reality, how big can your error be and how difficult it is? Expert opinion and guidelines are fairly easy to work with. They're obviously a bit dangerous. Simulation methods they can be very difficult, and there's various methods, the range, the critical path, risk factors, and the value. And they tend to sit there, and you end up normally using combinations of these. Then there's the parametrics. Easy to implement once you've got the model, difficult to develop the model done, but they are very accurate. They can be very accurate, especially for small projects. But for the sweet spot, you need to look at hybrids. So not one of these range estimation, you use it to apply to your critical path method, to your risk factors, but not really to your expected value, but not really to your risk factor. And you combine these and you get a bit of a better thing, because critical path doesn't have the cost element of it in yet, and so forth. So that's the one group of hybrids that you get. Then you get the other hybrid, which also works very well, especially in your early stages, is a parametric with a risk register, those few project-specific risks. And then the ultimate one is this one where you combine the simulation and parametric to get something. So typically, you've got a large mining project, you should have a combination of the simulation methods and a parametric for the systemic risks. And then you go get something that really predicts the reality.